All right, this is general and special senses. We're going to start by talking about our general sensory, our somatic sensory, and visceral sensory, and some of the ways that we categorize our different types of receptors. Then we're going to move into our special senses, going from simplest to more complex. We're going to find that olfaction and gustation, so taste and smell, are really pretty simple. But we're going to spend considerably more time on vision and hearing, also equilibrium, because equilibrium and hearing come from the same place. So we get more and more complex as we go through these different systems. And of course, I think a lot of our clinical relevance is really going to be down here in vision, equilibrium, and healing. There's clinical relevance in all of these, but this has the most complexity. We'll spend the most time there. You probably recall from integumentary system that you have a lot of general senses. You have the sense of touch from your skin. Special senses are going to be specific to cranial nerves, really, as how we're going to categorize those. I think your textbook is going to say all in your head, and I slightly disagree with that. But gustation, olfaction, vision, equilibrium, hearing are all special senses, and they're all going to travel along cranial nerves. This general senses breakdown, temperature, pain, touch, stretch, pressure, that should sound a little bit familiar from our pathways lecture from A&P1. Remember, we do have all these different general sensory inputs, and they actually go along different pathways, although we will not be revisiting pathways today. Now, sensory receptors, when we talk about general versus special sensory, we're just saying there are really specialized nerve endings, sensory nerve endings that have very, very specialized sort of dendritic ends. They can be very, very simple, like the dendritic endings in the nose, or it can be very, very complex, like the retina of the eye that has 9 layers histologically, and all of these different complex ganglionic cells interacting with each other. This should look like review to you. Remember that you have different sizes of receptive fields in different parts of your body. You have small receptive fields. Is that going to correspond with more sensitivity or less sensitivity? More sensitivity. So that means that one nerve ending is going to only innervate a small patch of skin, and another nerve ending is going to innervate a very, very close by patch of skin. So you're going to have more nerve endings in a small area of skin. And that's also going to correlate with more area in the brain dedicated to receiving that sensory information. Likewise, a large receptive field is going to mean that one sensory nerve ending is serving a large patch of skin or a very large area. Yes? Desmosomes loosely related, not directly. I think you're trying to connect the word somatotopy, and maybe that point-to-point connection. So remember, a dermatome is going to be a specific patch of skin served by a spinal nerve, whereas this is a nerve ending. So this is like a single branch. But that's a good question and a good connection to make there. Okay, so first new concept here. You've got a couple of different types of sensory receptors, broadly categorized. We're going to have more ways to categorize things than this, but this is one significant clinical thing about different types of receptors. Some receptors are tonic, which means that a sensory impulse happens and action potentials fire. A sensory impulse happens again, same number of action potentials fire every time. That's what you would expect, right? Is a sensation, a stimulus occurs, a sensation is had. But as it turns out, not all sensory receptors behave that way. You also have phasic receptors, where there's a stimulus, and in response to the first stimulus, there's a certain number of action potentials. But on the second stimulus, there's actually less of a response. Fewer action potentials are fired in response to that. And this is something that's real. This is something I can prove to you. One example of this would be, say you put on a wool sweater in the morning. And the first thing in the morning, that wool sweater is really itchy, right? But as the day goes on, you stop paying attention to it and you stop noticing that your sweater is itchy, right? Another example, one of my favorites is try smelling a pickle multiple times. Like, Take a pickle out of a jar or get a pickle with your sandwich for lunch today. Sniff it, put it down. Sniff it again, put it down again. Sniff it again. By the third time you sniff that pickle, I'm very serious about this, you cannot smell that pickle anymore. Pickle smell is gone. Don't believe me, try it. Highly recommend this process. And there's a really, really important reason for this. It sounds counterintuitive, but there's an important reason. I'll get to you in a second, Nadia. The reason for this is going to be evolutionary. And again, if you don't believe in evolution, you don't have to argue with me, you just have to learn it. Let's say you're sitting around a campfire and there's like all this overwhelming campfire smell, right? You need to be able to detect changes in the environment. You need to detect that like there's a tiger pissing in the woods over there. Like, this is actually really important to your survival. So a phasic receptor is about detecting changes in an environment and prioritizing changes over things that are already there. So things like your sense of smell, some of your tactile receptors are going to be phasic in order to tune out old sensations and prioritize new sensations. Does that make sense to you guys? Okay, Nadia, you had a question? Pickle smell would be phasic receptors. And that's just an example to solidify the idea. What you're focusing on here is this definition of tonic versus phasic receptors. Does that make sense to you guys? It's like if you get slapped in the face over and over again, that's pretty tonic, right? My wisdom tooth pain, that's pretty tonic. I'm going to go with tonic receptors for the dry socket situation going on right here. But yeah, a lot of them are phasic. Cool, right? Is anybody excited to go sniff a pickle later? Because I am. I wish I could eat pickles. I can't. Okay, properties, let's see. Receptors act as transducers. This is like a fancy physics word that means something really, really simple. We just change one form of energy into another. And this is going to be true for general and special senses. We're going to have, for example, you touch somebody's skin. That's a mechanical deformation, right? Like press that down, it mechanically deforms whatever deep pressure receptor is in there. It's a mechanical change. But your sensory receptor is then going to fire action potentials. Are action potentials mechanical or electrical? What are action potentials? Electrical, exactly, yeah. So we transduced from mechanical energy into electrical energy. So we're just using a fancy physics word to say we went from mechanical to electrical when we fired action potentials in response to a stimulus. And that's not the only way we transduce things, like from your eyeball, remember special senses, that's about light hitting the retina. That's light energy that we transduce into action potentials, which are electrical. So just that vocab word there. So far, so good? Good. Okay. All right, I think you're going to like classification of receptors. It's the perfect 8 a.m. topic. We can classify receptors by distribution, where it is. Is it somatic or visceral or special? We can go by stimulus origin. Is it a chemical? Is it light? Is it mechanical? And by modality. And again, I think you're going to love some of these vocab words. So by receptor distribution, we can say it's somatic and visceral. And we've already covered that concept of somatic versus visceral, right? If you get a cut on the outside of your body wall, are you going to be able to point to where that cut happened and be like, it's right there, it hurts? Yeah, you can do that. But if you had, let's say, an ulcer on your duodenum or duodenum, however you want to pronounce that, are you going to be able to say, oh, I definitely have an ulcer on my duodenum, I know exactly where it is, point right to it? Does that work out? No, it doesn't, because it's a visceral receptor, which tends to be non-specific. And then special senses, we can put under this receptor distribution sort of categorization method. I would just say based on cranial nerves. I don't know if I want to say they're located only in the head, but the ones that we're going to cover are located only in the head. Gustation, olfaction, vision, equilibrium, and hearing. Yes. Somatic receptors example would be all of the receptors in your skin, which we're about to talk about. So like deep touch, pain, vibration, light touch, all those things. Okay, stimulus origin, exteroreceptors are going to be external, and interoreceptors are going to be internal. What am I even talking about? Some of those interoreceptors are going to be conscious. Like you can have visceral pain and be conscious of it. Some of it's going to be unconscious though, right? You are not consciously aware of your oxygen saturation, right? You're not sitting here going, oh, I'm 95% O2 sat right now. I'm pretty good. But you do have interoreceptors detecting your oxygen levels, your carbon dioxide levels, your blood pressure, things that you're not conscious of. And we would categorize those as interoreceptors. And then proprioceptors, who can tell me what proprioception is? Yeah, where you are in space. So it's going to be located in muscles and tendons and joints. So even if your eyes are closed and you have no like external stimuli to tell you what your body is positioned like, you can still, do like this. You can tell I'm not on my Vicodin yet because I can still do that. Because my proprioceptors are working. Woo, rock and roll. It's your conscious knowledge of where you are in space. And these are some of my favorites because they're super obvious. Modality of stimulus. If a sensory receptor detects a molecule dissolved in fluid or a chemical, we call it a chemoreceptor. Who knew, right? If we detect change in temperature, we call that a thermoreceptor. If it detects light or color, it's a photoreceptor. If it detects mechanical deformation, pressure, stretch, that's a mechanoreceptor. If it detects changes to pressure, like blood pressure, or like how full your stomach is, for example, that would be a baroreceptor. So like a barometer if you're a fan of weather. Is anybody a fan of weather? They exist, I promise. I have some friends who are really into meteorology. Okay, so baro being about pressure. And then nociceptors are about pain. You know that nociceptors are about pain. You've already heard that term before. And then I have this prompter for you while you're studying. Try to come up with an example for each type of stimulus. Any questions about those? Those are the easy ones. I really like those. It's really hard to get those wrong on the test, right? It's like, I wonder which one of these is mechanical. Okay, questions, comments? So again, these are just different classifications. We can have modality of stimulus as a way of classifying things. We can have origin as a way of classifying things, or we could have distribution as a way of classifying things. It's just a lot of cooks in the kitchen trying to sort these things out. So just know the definitions of how we sort these things. Okay. So obviously pain has a lot of clinical significance for you. We're going to focus on differentiating, my thing's doing weird stuff, phantom pain and referred pain. So phantom pain and referred pain are not the same thing. So again, pain is nociception. It can be somatic or it can be visceral. Phantom pain is specific to, there's like a missing limb. Now, let's go back to that pathways lecture really quick. So let's say I was missing an arm. Let's say we cut off my arm. But this right here still exists. What's here? So sensory nerves, there's actually cell bodies for sensory nerves right here, all of them. DCML, spinal thalamic, they all have primary neuron cell bodies located in the dorsal root ganglion, right? Cutting off your arm doesn't change the fact that you have these cell bodies right here, right? So when you have phantom pain, it means that this neuron is firing despite not having that sensory stimulus come to it. That's all that means. So that's phantom pain. Referred pain is a very different thing. Referred pain means there's a sensory nerve ending from a visceral organ, so let's say the appendix, and then there's also going to be like a dermatome. There's going to be a spinal nerve serving a sensory map of just the skin, right? The body wall. When referred pain is happening, it means that a sensory nerve ending from the appendix is meeting up with a spinal nerve of a specific dermatome. It's hanging out, and then there's actually going to be crosstalk between these two nerves. So what you're looking at is this visceral sensory nerve fired, and that released its neurotransmitter into the synapse right there. But right next door is the sensory nerve ending from the umbilicus, right? So enough of that neurotransmitter drifted over to this dendritic spine over here and caused stimulation of that pathway. Instead of the visceral pathway, the somatic pathway was triggered. Is that clear? Does that make sense? So there's a couple of common sites of referred pain, and this is clinical relevance for you. So we just looked at appendicitis. The very common referred pain pattern for appendicitis is the umbilical region. Some of the weirder ones, liver and gallbladder, it can be localized to where the liver actually is, or it can refer pain all the way up to that shoulder. That right shoulder can be a site of referred pain for the liver and gallbladder. Here's the male distribution for heart pain. It's going to include that left pectoral region, that left brachium. It's that stereotype of a guy's having a heart attack and he clutches his left arm and goes down, right? That's only for men, though. Does anybody know what women are more likely to experience during a heart attack? Nausea, indigestion, possible. Where might they feel pain? In their back, all the way up in their neck is a possibility. There's one thing I was saying, if you guys want to confirm or deny from emergency medicine, if there's pain from here to here, you check for a heart attack, and what's that? In women, yeah, if there's pain anywhere from your jaw to your groin, basically, you're going to be concerned about a heart attack. So this research was done in men, and the PSAs went out for men. They didn't go out for women, and how weird heart attacks can be for women. And that's, what's that? Nobody knows exactly. There are some hypotheses floating around about embryology. For example, in the embryo, the heart is actually going to form within the neck and then go down. This is just like a conversation I had one-on-one with another anatomist where they were talking about, well, it's got a lot farther to go for men, so maybe, it being closer to the neck. In women, they drag with this dermatome, whereas in men, it drags along with this dermatome during embryological development. Yeah, it's got to be something related to dermatomes for referred pain. Yeah, what's up?
Some of it is due to the fact that the positioning of the heart changes with pregnancy. So that can relate to correlate with different dermatomes.
Probably.
After pregnancy.
Yeah, so changes over pregnancy. I'll just repeat it for the recording, but yeah, changes over pregnancy impacting that distribution potentially. Yeah, that's a good argument. So yeah, we don't know for sure. There are some hypotheses. There's some ways that people think about it. Yeah. Kidney pain is going to be like the entire flank, front and back, anterior and posterior. So I just focus on some of the weirder ones that are a little bit less intuitive. I think the stomach is nice and intuitive. I think, ovary and testes and genital pain is pretty intuitive. Question? I don't know. I'm really familiar with the heart being really different because it's sexist and horrible, and does lead to worse outcomes for heart attacks in women than heart attacks in men, since we all recognize heart attacks in men. Whereas a woman may not actually go into the ER for 3 days after a heart attack. but I'm not as familiar with the rest of these. I did not have this distribution for appendix pain when I had appendicitis. I had nothing even resembling this for appendicitis, for me personally. I just got up at 4 a.m. and started running around the house at the age of 12. And it felt better to be moving. I don't know why. As soon as I stopped, I felt bad. Yeah, it was not reasonable. So yeah, appendicitis is going to look different for different people. But yeah. Okay, any other questions before we keep going? Good questions so far. Thank you. Yeah. Yeah, so remember we've got visceral and parietal pain, right? What we're trying to do there, as I understand it, and this, since this is clinical and I'm not a clinician, I would double check my understanding, but this is what I've been told is we're trying to trigger somatic pain. Like it's visceral, it's not specific, we can't isolate it, but once that inflammatory thing hits the body wall, then we can start to pinpoint its location, as I understand it. Okay, your tactile receptors, we're going straight back to integument. This is going to be integumentary review right here. You have encapsulated and unencapsulated tactile receptors in the skin. This should look really familiar from our integument lecture. You've got some lamellated corpuscles down here. You've got some tactile corpuscles up here. You have some free nerve endings extending into the epidermis here. You have an end bulb, you've got a bulbous corpuscle, and again, these do have more up-to-date names. So I just went with all the standardized names. I'm going to repeat them now with the old school names that everybody else learned, just for the sake of the recording. So a lamellated corpuscle, this was traditionally known as a Pacinian corpuscle. This tactile corpuscle traditionally is known as a Meissner's corpuscle. This end bulb is frequently known as an end bulb of Krauss. And the bulbous corpuscle is often referred to as a Ruffini's nerve ending. Now again, for lab practical purposes, you can put either version that you're comfortable with. I just, again, as always, want you to be aware that the old school names are what everybody who's 5 years older than you learned. And so if you want to communicate with other people, you may need to know both. I used to really hate that free nerve ending picture. I need to just finally edit this and not do that anymore. Ignore that this picture is here. If I had time, if it was reasonable, I would delete that. I'm only going to test you out of the textbook images. I'm not going to introduce a weird one like this here. Free nerve endings, again, are unencapsulated. They do reach up into the epidermis, and that's going to contribute to a lot of things like sunburns hardening, right? A sunburn is just going to be that superficial layer of the integument. The fact that you have free nerve endings there that are going to receive pain information for you is going to contribute to that. Root hair plexus, you do have a plexus of nerves surrounding the hair root. So that's pretty intuitive in my opinion. Tactile or Merkel's discs, end bulbs of Krauss, light pressure, low frequency vibration, lamellated pressure, or lamellated corpuscles. I want you to focus on deep pressure for these. Bulbous corpuscles I think are really cool because they're like these elongated things in the dermis and they detect stretch. Skin distortion is how they phrase it here. I'm going to categorize it as stretch. So you can even sort of visualize that bulbous corpuscle stretching out and deforming and detecting that stretch, right? It's really, there's a lot of form-function connections here to be made. And that tactile corpuscle, that Meissner's corpuscle, that's really, really close to that epidermis. So again, discriminative touch is what they're saying. I'm going to say light touch for that one. So I have sort of done my big capital blue letters for what I categorize everything as and what I'm most interested in you learning from these things. The thing I'm most interested in you knowing about free nerve endings is pain. Lamellated corpuscles, I'm most interested in you learning about deep pressure. Ruffini's corpuscles or bulbous corpuscles for stretch, and tactile corpuscles for light pressure. That's what I want you to focus on. Any questions about those? Okay. So again, that should visually be review from AP1. We did cover those in AP1. All right, let's start our first special sense. Gustation. All of our special senses are going to be based on the same idea of sensory receptors. They're all just going to be very, very specialized. That's it. The only thing that we're learning here is what is special about it, right? What is different about the sensory nerve ending? It's not going to be a Pacinian corpuscle or a free nerve ending anymore. It's going to be its own cell type. Mostly we're going to call those cells hair cells. You're going to hear the word hair cell a lot today. Okay, so here's the tongue. One thing I do not care about is the difference between filiform, fungiform, and foliate papillae. I don't care about that at all. I don't think it's that important. There's some linguistics here for like, okay, foliate means like foliage, like plants, and fungiform, like kind of mushroom shaped. Filiform means kind of needle shaped. That's, no, I got nothing. One thing I want to say is the taste map is a lie. It's a complete and utter lie. It's a myth. There's no like, oh, the tip of your tongue is for sweet and the back of your tongue is for sour. That's a myth. That's a complete and utter myth. Okay, now I'm going to start pointing out stuff I do care about. One thing that's not on this image but will be important to you is that your tongue, the sense of taste, is served by two different cranial nerves. The anterior 2/3 of the tongue is served by cranial nerve 7. What's the name for cranial nerve 7? Facial, well done. And then the posterior 1/3 of the tongue is served by a different cranial nerve 9. Anyone? Glossopharyngeal, well done. Excellent, that was fantastic. Okay, next thing I care about. There is a difference between a papilla and a taste bud. This is probably the most frequently confused detail on this slide, is the difference between a taste bud and a taste papilla. So a papilla is something that's sticking out linguistically. It's a sticky outy bit, right? Remember the papillary layer of the dermis, for example. It had all of these peaks and valleys and peaks and valleys. That was papillated. So here's another papilla. The papilla are the bumps you can see on your tongue. You can open your mouth and say ah and see different types of papillae. These are all a specific type of papillae. All the little tiny bumps on your tongue are papillae. That is not the same as a taste bud. A taste bud is a collection of cells located on the lateral surface of a taste papilla. So we're talking about cellular structure, stuff you cannot see with the naked eye when we talk about a taste bud. I know that's really counterintuitive to what you've been taught like all of your lives, right? Okay, so what's happening when you taste food? There's saliva, and it's going to liquefy the molecules, or you're going to liquefy the molecules of your food. And that saliva is going to bring the molecules of your food along the lateral surface of the papilla. And there's going to be this little taste pore right here. And that's going to expose little taste hairs. So let me zoom in effectively. So this is, we've taken taste bud, we've kind of flipped it 90 degrees. So here's the taste pore now. And you're washing molecules over this taste pore, and then you have these little taste hairs. There's going to be an issue between cilia and microvilli today. The taste hairs are effectively microvilli. What's the purpose of a microvillus or microvilli? Increased surface area. Okay, so those taste hairs are going to be a surface for the molecules in your food to attach to. And they're going to be covered with different types of receptors. We're talking about receptors for neuroscience, right? And the attachment of different types of molecules like sodium, like hydrogen, like glucose, like different amino acid chains, protein, that's going to trigger taste cells, which are in the taste buds, to trigger action potentials in this, whichever cranial nerve this is. Cranial nerve 7, cranial nerve 9, depending on where on the tongue. Okay, so again, back to here, you've got your gustatory cells. That's that specialized modified sensory cell, which has the microvilli, the taste hairs, and that's the one that can trigger the action potential. You can also see here, you've got some support cells. So they're going to be supporting cells, there's going to be hair cells. You're actually going to see this as a pattern in most of our special senses. There's going to be a cell with some kind of hair coming off of it, and there's also going to be supporting cells next to it. In this image in particular, I want to clarify the supporting cells are sort of a darker color. The actual gustatory cells are a paler color, and they are attached to these sort of yellow tinted nerve endings. And that's how you can distinguish the actual gustatory cells versus the support cells in that image. Okay, is this a taste bud or a taste papilla? That's a papilla. Is this a taste bud or a taste papilla? Taste bud. What type of cell is the one I'm on right now? Gustatory. And what type of cell is that? Support. Good. There are also going to be some basal cells. We're not going to really worry about their functions, though. And these, again, are just different representations of the same idea. So again, gustatory microvilli are going to be synonymous with taste hair, depending on how informal you want to be. That taste hair extends through the taste pore, again visualized right over here, this space. You can only detect 5 flavors: sweet, salty, sour, bitter, and umami, which is a Japanese word that just means like protein. All of the rest of your sense of taste comes from smell. You've probably heard that before. If you've got a cold and your nose is stuffed up, everything tastes really bland, right? Because so much of what we perceive as flavor is actually smell. Let's see, this is cranial nerve 7 and cranial nerve 9. Which level of the brainstem does cranial nerve 7 have a nucleus in? Is it midbrain pons or medulla oblongata? It's in the pons. Good. What about cranial nerve 9? Medulla oblongata. So good. I'm so glad all of you guys. You're doing so awesome with the neuro. So here you've got these 2 different pathways, and it's just saying, okay, here's cranial nerve 7, here's facial, and that's going to the pons before it's going to go to the gustatory cortex. And then you have cranial nerve 9, and that goes to the medulla oblongata before it goes to the gustatory cortex. Where's the gustatory cortex? And the insula. Yes, so good. Gustatory cortex of the insula. Really, really happy with you guys. So again, yes, there's a pathway to learn here, but you already know big chunks of it because you worked really hard for neuro, right? One thing you may notice missing from this is spicy a flavor? No, spicy is not a flavor. Spicy is just pain. I know, it makes me sad too. Spicy is just pain, and pain is actually going to be served by trigeminal. Remember, trigeminal does general sensory for your face, and that includes your tongue. So if I'm like trying to sort of fit all of these cranial nerves into their place, I always just kind of go 5, 7, 9. So like they're all odd numbers, they stack up in order, right? 5 for spicy, 7 and 9, 7, 9. Endorphins, that's a good question. Pain causes the release of endorphins, is a big part of it. Some people say it makes it more flavorful. There are flavors in peppers aside from capsaicin and pain, but scientifically speaking, the only flavor that spiciness itself imparts is pain. Yeah. Right? Okay, I actually want to stop there. It's a little early for a break. but we're on to a new topic. So